Good afternoon, ISMAR 2022 members. I'm Dorzhieva and I will present DroneARchery, human-drone interaction for augmented reality with haptic feedback and multi-UV collision avoidance driven by deep reinforcement learning. The research is focused on human-swarm interaction. Swarm robotics is a leader in patient activity across robotic space. The advantages of a swarm of drones in monitoring tasks are obvious. Many companies around the world use them in agriculture, pollution monitoring, relatively new applications, rescue operations, firefighting. A lot of research is currently underway on drone swarm control, including ways to deploy it quickly in any area. What's next? Drones could find applications in the rapidly evolving metaverse. 2022 studies shows that funding could reach $13 trillion. The transition of drones into the metaverse will not be possible without the visual or tactile feedback necessary for precise control. Its combination will increase not only the level of accuracy, but also the naturalness of control. Scientists have conducted research on how to improve the control of a swarm of drones. It is relatively easy to control a single drone with a joystick, but it's challenging to control a swarm. There is no intuitive way of understanding how to point the swarm of drones on tangible objects in the way of targeting. We propose the DroneARchery technology, intuitive interaction with drones supported by tactile feedback for real-time swarm trajectory generation and formation control. The novelty of the project is the augmented reality-based framework with the haptic feedback for human-robot interaction driven by reinforcement learning. We developed a novel concept for intuitive drone control with the high-quality positioning and operator training in a game scenario, DroneARchery. Also, we developed a reinforcement learning-based collision avoidance and drone swarm control for environments with fast-moving obstacles. Let's look at the system as a whole. We propose the concept of rapid deployment of a swarm of drones. In the video, you can see the user. The user controls the drone's trajectory by shooting from a virtual bow. Like in real archery, ballistic trajectory depends on the position of rounds. At the moment of aiming, the drones follow the palm. The trajectory, direction, and range depends on the position of the palm, like in real archery. In the picture, you can see 4 proposed human-robot interaction scenarios according to DroneARchery technology. We suggest users to perform swarm deployment with or without haptic display and visualize drone trajectory in the Oculus headset. Motion capture system tracks palms in gloves. We use Vicon. Haptic display conveys the feelings of the bowstring tension. From this, user can understand the range of trajectory. In augmented reality, the user views trajectory. The user can deploy a swarm by directing drones one by one or several at once in the formation. The swarm of released drones dynamically avoids collision between each other with behavior control based on reinforcement learning. Haptic interface is a display that transmits tactile feedback to the user's forearm. We utilized a haptic display inspired by the Link Touch technology. In this display, the user can estimate the pulling force. While users can aim naturally by directing their hands at the target, they have no natural means to estimate the pulling force as it is calculated entirely virtually. The tactile interface solves this problem and makes the goal achievable. We evaluate the ability of users to recognize the tactile feedback. We developed 12 patterns that represent the bowstring tension and the bowstring stiffness. We demonstrate to the user's pattern with comments indicating distance and applied normal forces of haptic display. We separate visual and sound feedback from the haptic display from the user by headphones with white noise and screen. The haptic interface reproduced patterns in a random order 3 times, with a 10-second time delay between every pattern. Users predicted patterns. Here from the right side you can see the proposed patterns for distances of the contact points and two types of pressure, light, medium, and strong. And from the left side you can see results with the conclusion matrix that we get from this experiment. And we can say that the user demonstrated the ability to distinguish tactile patterns produced by the haptic display representing varying ghosting tension and the ghosting stiffness. Next experiment was provided to evaluate the proposed technology for swarm deployment. On the picture, you can see four groups of users that control the drone with different interaction scenarios. Some of them have haptic display, some of them observe visualized trajectory in Oculus. The aim of users was to earn the maximum number of points in the archery game. The task would be accomplished by deploying the drone from virtual ball in 3 gates of different sizes. The scoring policy was as follows. In each of the 3 gates, it was required to fire 3 shots. If the shot was successful, the user earned 1, 3, or 5 points according to the size of the gate. Thus, the maximum number of points was equal to 27. Users evaluate the system with Likert scale, answering the next question. How natural was the tension station of the virtual ball? Was the goal achievable? Was it physically difficult for you to fulfill the game? And did the drone fly in the expected direction when released it from virtual ball? The group that was most successful was able to both use the drone's flight path and feel tactile feedback. The system improves trajectory prediction accuracy by 63.3 for applying AR technology and conveying a haptic sensation of the pulling force. It's group 4. DroneARchery users highlighted the nationals 4.3 out of 5 and increased confidence 4.7 out of 5 when controlling the drone. In addition, we compared the average scores earned by users with and without experience with AR interfaces or drones. And results supported our hypothesis that experience with AR did not significantly affect users' performance. Now let's imagine a real situation. We release a swarm of drones using DroneARchery technology. And by mistake of the user, he released one drone into another which is already on the field. In this case, we need to provide a collision avoidance algorithm. We will solve this problem with a reinforcement learning approach. We create a custom environment for training the algorithm and OpenAI gym. The environment consists of Asian drones that must avoid colliding with the other drone and its neighbors. Then we play several episodes in the environment with the drone arrow flying along a ballistic trajectory. Next step is a simultaneous playback of episodes and training of agents using the actor-critic method. Actor learns to provide actions of agent's velocity, and critic learns to correctly assess the state of agent. The next experiment we provide in simulation. Drones survey information, and one drone breaks this information by flying ballistic trajectory. The task of drones information is collision avoidance with drone arrow and each other and environment borders. Results shown show that swarm of drones dynamically avoids the one drone deployed by the user and external obstacles in 96%. The comparison reinforcement learning approach with artificial potential field showed that the average execution time is approximately the same, and it means that algorithm can be applied in the real-time implementation. So let's summarize our results. The novel interface for intuitive drone control with operator training in a game scenario was developed. The accuracy of hitting the target was increased by 63.3% among users using the haptic display and AR technology. Users demonstrated the ability to distinguish tactile patterns produced by the haptic display representing varying force and tension and stiffness. The reinforcement learning-based algorithm shows the best time to calculate the trajectory of 3 drones in comparison with artificial potential field. The novelty of the research is the development of AR-based approach for drone control that does not require special skills and training from the operator. In the future, the proposed interaction can be applied in various fields, for example, for fast form deployment in search and rescue missions, crop monitoring, inspection, and firefighting. Moreover, drones are finding application in the rapidly evolving metaverse. For the future work, we plan to increase the number of agents in the swarm and conduct experiments with the remote deployment of drones.